Now, depending on how many questions that you have regarding proofs, we could easily spend the whole class going over questions on the board, but we don't have that time, right? So we got to find a balance here between being fair to you and going over questions you have and then saying at some point, we got to move on. So does anybody have any questions you would like me to go over? Jonathan? 13? I'm assuming it's on the first set, page 33 to 36. Okay. Is it this one? 13. This one. Okay, so I'm going to now just mention to you that we always say if you converted everything from sine to cosine, it's going to probably work. But there sometimes are other things you can do. So as I looked at this question when it came up, Jonathan, I saw 1 minus 2 sine squared there and 1 minus tan squared, and I thought maybe I can start using Pythagorean identities. Okay. And that's certainly a possibility, because if I look at my formula sheet, I don't know. I think 1 minus tan squared is equal to something, but no, I'm mistaken. It's 1 plus tan squared. So that throws that idea out the window. I think we could probably still work with Pythagorean identities somehow, but I'm going to choose not to do that. So what I'm going to do instead is go with my initial idea of putting everything in terms of sine and cosine. So on the right-hand side, I have 1 minus 2 sine squared of x. And on the bottom, I have 1 minus tan squared, which is sine squared of x over cosine squared of x. Is that okay so far? So again, if you were doing this as an official proof, you would write that you've used a quotient identity here. Now what we're going to do is, and here's my motivation for working on the right-hand side. The left-hand side is simply cosine of x times cosine of x, so it doesn't get much simpler than that. I could write the left-hand side as 1 minus sine squared, but I don't really have a motivation for doing that, at least not yet. So over here, I'm going to multiply the top and the bottom of this expression by cosine of x. And I'm going to get 1 minus 2 sine squared of x times cosine of x. And I'm really holding off here, Jonathan, on deciding to multiply that cosine through. I could multiply it through, but then if sometime later I decide that wasn't the best option, I have to factor it out, and factoring is more work than multiplying it through. So if I need to multiply it through, I will. On the bottom, I have cosine of x minus sine squared of x. And I'll be honest with you, up until this point in time when I just finished writing that, oh, my mistake. We got to multiply by cos squared, don't we? Good? Okay. So I just want to double check now because I didn't see it was squared. So I'm multiplying top and bottom by cos squared. Here the cos squareds cancel, so I'm left with cos squared minus sine squared. It's good now, I think. Okay. At this point in time, and I really wasn't sure where this is going, but since everything on the left-hand side is in terms of cosine, I'm just going to rewrite everything on the right-hand side in terms of cosine. And I can do that because wherever there's a sine squared, I can put 1 minus cos squared. So what I'm going to have is 1, this is going to get a little messy, minus 2 times 1 minus cos squared times cos squared, and it's over cos squared. This whole thing is times cos squared. It's over cos squared of x minus sine squared of x, which is 1 minus cos squared of x. So what I've done here is where this sine squared of x was, I put 1 minus cos squared, and where this sine squared of x is, I put 1 minus cos squared. There's, by the way, I just realized there's a much simpler way to get to the answer. Does anybody see it? I'm not going to erase my work because some people might be looking at this and they might want to proceed. I'm just going to say we don't need to do that. Shazmaida, do you know what we can do here?
I was thinking because 1 minus 2 sine squared x is identity already.
Right. 1 minus 2 sine squared x. I'm working on the right side here, Jonathan, but I'm just writing my work over here for instructional purposes. 1 minus 2 sine squared of x is cos 2x, isn't it? And then we have times cos squared of x. On the bottom, cos squared of x minus sine squared of x is also cos of 2x. And we're done. I mean, we were very fortuitous here in stumbling on this. I actually, back up here, when I saw this, I didn't say anything, but I was thinking, wow, man, maybe we should write cos 2x. But the reason I didn't pursue that immediately is I thought, how's that going to help? Because I don't see cos of 2x anywhere else. It turns out it appeared. Is that okay? Okay. I don't know what would happen if you pursued this further. I suspect, well, we're so close to being done. If I expand the top, I have 1 minus 2 plus 2 cos squared x. So I'm just multiplying that negative 2 through. And then I have times cos squared of x. On the bottom, I have cos squared of x minus negative cos squared of x, which is 2 cos squared of x. And then I have minus 1. This is the same as this, so they cancel. Again, there's not one way that you have to proceed to the answer. It's just that you have to use math properly. You have to use algebra rules properly, identities properly. Any other questions before we move on today? I would encourage everybody to get more practice with this. I know that if you're like me, a 4-day weekend, at the end of the day, I just kind of shut down in terms of schoolwork, but you should probably do some of this stuff over the weekend. Yeah. Absolutely. Yeah. So we're going to move on right now and take a look at lesson 6.4, which is it's not really a complicated issue that we're dealing with here today. You already know how to solve trigonometric equations by either factoring them into linear equations that you could set equal to 0, or by using your unit circle, or by using, for some of us, a reference angle approach and then finding angles that fall in those particular positions where the reference angle tells us the terminal arm is. And we already know how to work with identities, recognizing, for example, as Shazmaida did, that 1 minus 2 sine squared of x is the same as cos of 2 of x. We're just putting this together now. And I can summarize what we're learning here is that we're going to be rewriting trigonometric equations that are complicated into simpler trigonometric equations using identities. You know, one of the most basic examples I could give you would be something like sine of x over cosine of x is equal to 1 over root 2. This is almost too simple, but it drives home the idea of what I'm talking about. We're going to take an equation that's complicated, which is what you're looking at, and make it less complicated by writing tangent of x equals 1 over root 2. This equation would not have been given to you when we first learned equations, because it's got a mixture of sines and cosines, and you don't know what to do. This equation would have been given to you when we first learned about solving equations. And by the way, let's just solve this first of all. You don't have to write this down, but this is a positive number. So if you're talking about quadrants, this means it's in quadrant 1 and quadrant 3. I'm going to go with a unit circle approach. No, I guess we can't go with the unit circle approach. And let's say that this is meant to be in degrees. So everybody just do me a favor. That number, by the way, is on your unit circle as a number that we know, but it's not a tangent. It's a y or an x. So do me a favor and take your calculator and find a reference angle here if you go inverse tangent of 1 over root 2. So this example that I've just thrown on the board is kind of an off-the-cuff example. Make sure you are in degrees, and we get 35 degrees. So you get 35 degrees, yes? Okay, well that means we're going to draw a reference angle of 35 degrees in quadrant 1, a reference angle of 35 degrees in quadrant 3, and then you would find the rotation angles by using your knowledge of reference angles and quadrants. In quadrant 1, the rotation angle, angle x, would be 35 degrees. Here it would be 180 plus 35 degrees, which I think is 215 degrees. But I hope you catch my drift that when you look at this, you don't know how to solve it. Well, you do, I guess, now. You look at it and you say, in order to solve it, you're going to change it into this. That's the goal here. Okay? So let's take a look at the examples. Solve each equation. Sine of 2x minus cos of x equals 0. This is an impossible equation to solve in its current form. We have to rewrite it somehow, and it's reasonable to expect, I hope, that you're going to look at sine of 2x and say, well, it must be that I'm going to write 2 sine x cos x. That's the only thing you can do here in terms of changing the appearance of the equation. Minus cosine of x equals 0. I won't go back and show you, but I believe this is actually one of the examples we did when we learned how to solve trigonometric equations in the previous unit. In this particular case, we can factor a cosine of x out and be left with 2 times sine of x minus 1. This is equal to 0. And again, everybody, I want to point out the general philosophy I have with stuff in math in high school. This is difficult. By changing it into this makes it doable. Is that a word? It is. I thought I was making up a new word. This becomes easier. And then as soon as we write cosine of x equals 0 and 2 sine of x minus 1 equals 0, we're now in the territory of stealing candy from a baby. It becomes quite simple, or it should. Because really these two equations, everybody, are actually Math 20-1 equations now, right? So very easy. And that's, I think, a very important philosophy for you to have as you're working through math in high school and maybe post-secondary, is you use your skills to turn things into simpler problems. Anyway, I'm not going to be doing these with a reference angle. This equation becomes sine of x equals 1/2. We have cos of x equals 0. Don't forget that cosine is the x coordinate on the unit circle. Sine of x, sine of the rotation angle, is the y coordinate. These are both, when I say x coordinate and y coordinate, I mean on the unit circle. So what we are looking at here is having a circle that's a unit circle and saying where on there is the y coordinate 1/2. The y coordinate is 1/2 here, which means at this location and at this location. Where is the x coordinate 0? Well, the x coordinate is 0 at this location and this location. So we've figured out the locations. Now we need to determine the rotation angles. Can you let me know, Reagan, does it say 0 to 2 pi radians? Okay. So we're going to start at 0 and we're going to rotate to all of these angles. How many radians to there? How many radians to here? How many radians to here? And how many radians to there? Should have just drawn these. Well, the first one, and I think if I did what I'm about to do, it's confusing, it's cluttered. I mean, we have to find this, we have to find this, we have to find that, we have to find that. I don't want to do that. I know I just done it, but I'm going to erase it, okay? You should be able to understand that when we talk about rotation angles, that's what's going on. So what is x for the rotation angle for the first point, which is here? It is pi over 6. For the second point, which is up top, is pi over 2. For this third point will be 5 pi over 6. And for the last point, it's 3 pi over 2. Any questions with example 1? So you will note as well for example 1, and there's a part B, if you go to page 317 of your textbook, there's a similar set of problems. Let's try B now. 2 cos x plus 1 minus sine squared x equals 3. The reason why this is not solvable in its current form is it contains a mixtures of sines and cosines. And it's a different kind of mixture. Admittedly, this one we turned it into a mixture of sines and cosines, but we could factor the cosine out. Here we have sines and cosines and numbers. And we run into this a lot. What we can do is, since sine squared of x equals 1 minus cos squared of x, I can put in here this thing and get 2 cos x plus 1 minus sine squared of x, which is 1 minus cos squared of x, equals 3. Okay? And that's going to simplify to 2 cos x, and then we have plus 1 minus 1. Well, that's pretty good, because 1 minus 1 is 0. Then we have minus negative cos squared, which is plus cos squared of x. Now, I do understand that, for example, Marcel brought this up a couple days ago. Marcel said, in this particular case, couldn't we say that cos squared of x is 1 minus sine squared of x? And 1 minus sine squared of x is right there, so couldn't we just cut to the chase and put cos squared of x in? Does that You're following me there, Marcel? And the result is the same thing, but again, I just want to caution you because sometimes this number will not be 1, and then it doesn't work. You can always, by the way, and I haven't mentioned this, if it's 2, you can write it as 1 plus 1 minus cosine squared and do a substitution. Anyway, we're left with this equation. I'm just going to rewrite it as cos squared of x plus 2 cos of x equals 0. And then we can factor it and solve each factor. Yeah. Oh, thank you very much. This is not equal to 0. Thank you, Reagan. It's equal to 3. Well, the mistake I just made there is a pretty common one that you want to try to avoid. Yeah.
How did you get from negative close to positive?
What I'm doing here is I'm subtracting this. The question is, how does it become positive cos squared? So you can think of subtracting everything inside. There's a lot of ways you can handle it as you remove the brackets and change all the signs. That's what some of you might do. That's kind of a junior high way of thinking of it. If you think that way, I'm not criticizing you. I'm just saying that's initially how you were taught this. I prefer to think of it this way, that you have to take this negative 1 and multiply it by each of these two, and that's why the signs switch. So now we're good to go. This is quadratic. Had I realized it was 3, I probably would have moved the 3 over in the last step. Anyway, we have cos squared of x plus 2 cos of x minus 3 equals 0. And this is a fairly basic trigonometric equation to factor and solve. It's not quite in the Math 20-1 realm yet. It's still Math 30 because it's quadratic. But this will factor into cos x, and cos x being the leading terms of the two binomials. And what two numbers multiply to give negative 3 and add to give positive 2? Those would be the numbers. Are we in agreement on that? All right. If it's written response, I suppose you probably should write this before you write this. But I don't know, that's kind of even iffy. I mean, if cos x plus 3 equals 0, you know cos x equals negative 3. And then we could write cos x minus 1 equals 0, which leads us to cos x equals 1. So if you are a unit circle kind of person, and I guess I'm kind of forcing us to think of the unit circle if we're allowed to. We have the unit circle, which has a radius of 1. I'm going to do that again. We have a unit circle. What's going on there? With a radius of 1. So the radius of this is 1. Cosine is the x coordinate on the unit circle. So dealing with this equation first, where is the x coordinate 1? Right here. Dealing with the second equation, this one, where is the x coordinate negative 3? Nowhere on the unit circle. And you can imagine that this is the case, that cos x equals negative 3 has no solution as well. You can figure out that that's the case because we've learned that f of theta equals cos of theta. I'm avoiding the use of x's and y's on this graph, okay? F of theta equals cos of theta has a maximum of 1 and a minimum of negative 1, and it does this, right? So is cos of theta ever negative 3? No, it only drops to negative 1. And that means that this question has turned into a real simple solution. The answer is that x is equal to 0 or 2 pi, but I need to look carefully at what my domain said, like where are the equals to in my domain. Oh, x can be equal to 0 and x can be equal to 2 pi, which means we have two solutions. Any questions with B? All right, number 2, sine squared of x equals 1/2 tan of x cos of x, and we want to solve that in degrees. I just have a question for you. I mean, this is kind of like, I think I used the analogy yesterday of seeing the matrix. How many of you look at tan x cos x and don't see that? You see something else. It's sine x, isn't it? So the idea here is we've actually got three different trigonometric ratios. We have sines in there, we have a tangent in there, and we have a cosine in there. We want to get everything to be the same, ideally. Not always, but in this case it will work. So if I rewrite this as sine squared of x equals 1/2 sine of x over cos of x times cos of x, the cos of x's will cancel, and I'm left with a trigonometric equation that contains only sines, which means it's simpler in some way. It's less complicated. I end up with sine squared of x equals 1/2 sine of x. I would immediately say, man, I don't really want to work with fractions unless I have to. So I would multiply both sides of this equation by 2 and get 2 sine squared of x equals sine of x. I'm multiplying both sides by 2. I almost wrote 1/2 sine of x, but the half is gone. That's why I'm multiplying by 2. I can subtract it now. Because it's quadratic, I need to zero the equation. Now I can factor out a common factor of sine of x. Which means that sine of x is equal to 0 for the first factor. And for the second factor, sine of x is equal to 1/2. And I think a lot of us have graduated to the point where you can almost picture the unit circle and tell me where these angles and locations are. But again, I'm still going to draw it. If you wanted to use a reference angle, I can't stop you from doing it, but I'm encouraging you not to. Don't forget that sine, despite the fact that it says sine of x, sine is the y coordinate. Remember that x is an angle in this context. And this is a y coordinate because it's sine. So where is the y coordinate 1/2? About here. So these two locations. Where is sine 0? Well, that's where the y coordinate is 0. So these two locations. I now want to take a look at the domain in this question. The domain was, degrees can be equal to 0 or greater than 0, but it has to be less than 360. So my solutions will be, I guess I can draw in my arms here. That, and that. The first one, the first one is 0. So x equals 0 degrees. Then 30 degrees. Then 150 degrees. Then 180 degrees. And then we could go 360 if it weren't for the fact that the domain doesn't include 360. Any questions with number 2? As I said, I don't think this is very taxing on our brain. I'm not sure why I don't have number 3 up here. Thank you. So number 3, we have cos of 2 theta equals cos of theta. And we want a general solution. Did I write that down correctly? Because I can't read small print with these glasses. Okay. Go to your formula sheet. You have 3 identities for cos of 2 theta. And I want you to find out which of the 3 identities for cos of 2 theta we should use to remove cos of 2 theta. Cos of 2 theta is equal to 3 different things. Wow. Is equal to 3 things which are all identical but written differently. They appear differently. To how many of you is it, maybe obvious is the wrong word, but you take a look at them and you go, oh yeah, I think I'll try this one. Which one do you think, Jonathan?
Would it be a second one?
Can you say it out loud for me? Because I don't know what order they're in.
2 cos squared of x minus 1.
Definitely. And in this case, we're using theta. So it would be 2 cos theta, cos squared of theta minus 1 equals cosine of theta. Jonathan, can you tell us what your reasoning was? That's what I would do as well.
Because then we could subtract the cos beta.
Okay, so I'll start with that. We can subtract the cos theta and get 2 cos squared theta minus cos theta minus 1. What would you do next? You don't have to tell me what we would get, but what would you do in general?
We would then basically factor out that whole equation.
That's right, we could factor it. The problem is if you chose one of the others, like sine squared minus cos theta, then you're going to have a quadratic equation that contains sines and cosines, and you can't factor that as a quadratic equation in one variable. Even though there's one variable theta, you have sines and cosines and it clutters things up. The same with putting in 1 minus 2 sine squared. Then you're going to have a mixture of cosines and sines. So since we had on the right-hand side cosine, we want to choose a substitution that also has cosines. We can factor this. Let's see, 2 cos theta. I'm assuming it's factorable. It's got to be 1 and 1. We want, when we FOIL this out, to get negative 1 cos theta. So I believe if we do this, FOILing it out will give us, for the outer product, negative 2 cos theta. And for the inner product, positive 1 cos theta. And this gives us this. Yeah.
Would we ever have to use quadratic?
It's a good question. And as I was writing this out, I said, and I'm pretty sure this is factorable. I thought, I guess I have to address that. The question is, and I've got a little bit of an error here. I should write equals 0. Are we ever going to run into situations where we have a trigonometric quadratic equation, but it's not factorable, but there are solutions? I think you might run into it, but you could always solve it graphically and get decimal answers. I have never seen, and I don't think you would be expected to apply the quadratic formula. By the way, if you did apply the quadratic formula to, and I'm only speaking to you now as a Math 31 person, let's say you had 3 cos squared theta minus 4 cos squared theta, or 4 cos theta minus 1. I think that's not factorable. If you do the b squared minus 4ac thing, I think you get 28. So we're taking a little side journey here for my Math 31 students. 28. So when you use the quadratic formula, this is equal to 0, you would have the solution is negative b plus or minus root 28 all over 6. Are you with me on that? Okay. But here's the thing, Marcel. That's not theta, that's not x, that's cos of theta. So, and in terms of the rest of us, this isn't hard to follow. If you figure out what this is, if you go 4 plus root 28, and then you divide that by 6, you get a number outside of the range of cos of theta. So one of your equations would be cos of theta equals 1.54, but there's no place on the unit circle where the x coordinate is going to be 1.54. There's no reference angle. If you went inverse cos, it wouldn't work. I'm hoping that if we go 4 minus root 28, I thought about these numbers before I put them in, good, and then divide by 6, we get that. So then you would be solving cos theta equals negative 0.215. You'd find a reference angle. You would look in quadrants 2 and 3 because cosine is negative there. So you could potentially see that in Math 31. Okay. Any other questions with that example so far? I mean, we're not quite done. The rest of it will be pretty simple. The first factor gives us cosine of theta equals negative 1 over 2. The second gives us cosine of theta equals 1. Again, cosine is an x coordinate. I think this is important, and I don't remember either in this course or in the past when I've taught it writing that, but I'm going to get in the habit of writing that every time, what I've written in green. So when you look at the unit circle, a little bit of a flattened one, but that's okay. Cosine is an x-coordinate. Remember the radius here is 1, so the x-coordinate of negative 1/2 will be here and here, these two locations. Cosine is 1 when the x-coordinate is 1. So you are looking at 0, 2 pi over 3, 4 pi over 3. I want to take a peek to see if we're working in radians or not. We are working, I cut it off. Does it say radians? Okay. But it says a general solution, right? Okay. So I could, everybody, say this. I could say, what's going on here? There we go. I could say 0 plus multiples of 2 pi, 2 pi over 3 plus multiples of 2 pi, 4 pi over 3 plus multiples of 2 pi, and put all of these with an n is an element of the integer number set. And by the way, for the 0, you don't need 0, right? You could just put 2 pi n or 2n pi or n2 pi. So before I finish this one off, because there's one other little detail that I want to talk about, does anybody have any questions about the connection between the solutions that I have written at the bottom here and the diagram showing the unit circle? Okay. We don't have to write the solution that way. What we could have written is this. We could have said multiples of 2 pi over 3. Only because in this case, this is 2 pi over 3. This is 2 pi over 3. This is 2 pi over 3. And it's interesting because you see questions on diploma exams and my exams where it actually gives you the equation, and then it says there's 4 people, and Alice wrote this. and Betty wrote this, and Charles wrote this, and Danny wrote that, who's right? And both Alice and Betty are right. There's different ways to communicate the answer. All right, let's take a look at the last question and finish this lesson off. This looks pretty confusing, but I don't think you have too many options here. 3 cos x plus 2 equals 5 secant x. Well, I only see an option of changing that secant to 1 over cos. I don't know what else you could do. The only thing else you could do, to use my road analogy, is to just stand in the road and stare at your surroundings. So literally what I'm talking about somebody doing here is just staring at the question, hoping against all hope that something magical is going to happen in your brain and you're going to see the answer. And it doesn't work that way. You got to try. But I have a fraction in an equation now, and I don't like fractions. So I'm going to multiply both sides by cosine of x. I'm just making a note for myself about something. So I'm going to multiply both sides of this equation by cosine of x. And then on the left-hand side, I'm going to get 3 cos squared of x plus 2 cos x equals 5. Does that look okay? Yeah.
Do we have to write that it's a reciprocal identity?
No, that's a good question, Shazmaida. When we're doing proofs, we have to write the name of the identity that we use in our work. When you're solving an equation, you don't have to. But you know what? Nobody's ever asked this before. I think if you were solving an equation here, I think what I would do at this point where I've substituted 1 over cos, I would just put this on the side. Because the whole point of solving an equation algebraically is showing all your work. So rather than writing the name of the identity, which I think could work, I think this is actually a good idea. In fact, I take back what I said. I think you need to write something to justify it. And think of it this way, everybody. I think to most people, I hope, to most of us, that this is obvious. You don't even have to think about it, but you want to be careful that this is Math 30-1 and we are learning complicated ideas. So what becomes obvious is not necessarily obvious to everybody. So you should communicate it. We're going to subtract the 5 from both sides and get 3 cos squared x plus 2 cos x minus 5 equals 0. I sure hope this is factorable, otherwise what I told you a second ago is a lie. I believe it's factorable. We can do the b squared minus 4ac test. Remember, if the discriminant b squared minus 4ac is a perfect square, it's factorable. I think we're going to get 64, which is a perfect square. So we can go ahead and factor this. The nice thing about factoring this one with trial and error is there's not really too many options. It's got to be 3 cos x and cos x. And the numbers have to be a 5 and a 1, so it's just a matter of playing around with the location of each. And I think with a little bit of thought, you can see the 5 is going to go here and the 1 is going to go there. This will give us a 5x in the middle, well, a 5 cos x for the inner product. It will give us a 3 cos x for the outer product. We want positive 2, which means the 5 has to be positive, the 3 has to be negative. We can trace things back to how we got them, and there it is. This, of course, is equal to 0. And we're so close to being done. How many of you see right now, before you even write down the next step, that the first factor will not have any solutions. So what's starting to happen here, and I talked about this, I think it was in calculus yesterday. Most people, I think, picture it in their brain before they write it down, or as it's happening. So as I'm writing this down, I'm going, well, the next step is going to be to move that 5 over and divide by 3. But that is a cosine value of negative 5/3, which is outside of the range of values of cosine of theta. Cosine of theta goes from negative 1 to 1. Whether you talk about the graph, it goes from negative 1 to 1, or you talk about the x-coordinate on the unit circle, it goes from negative 1 to 1. So there's no solution here. But the other one is cosine of x minus 1 equals 0, which means cosine of x equals 1. Reagan, just help me out because you're right here. Was this a general solution?
Yeah.
Degrees or radians? Radians. So the only place that cosine of x is equal to 1 on the unit circle is right here. So I guess we can just say that x is multiples of 2 pi. Where the multiple is an integer value, and integers include 0, so that would include 0, 2 pi, 4 pi, negative 2 pi, etc. Any questions with that final example? So what you are doing here is, in the textbook, page 320, there's a set of suggested problems. You are taking parts of the equation that look complicated and using identities to rewrite them in some other form. There's supplemental practice as well. I don't know. I would have to take a look at these. This is my comment from last time I taught the course. On page 29, number 2i and 2j are tricky. And I'm curious now because on page 25 I'm saying number 4b is absolutely dirty. It's a dirty question. It's a rotten question. I'm going to take a look at it just out of curiosity, though. So get to work on that. I will come around and help you out shortly.